Can you hear me in the back, Rob?
Yeah.
Yeah. Too loud?
No, it's fine.
No, no. Okay, good. Be careful. Okay, another week, another lecture hall. Good that you all found it. Actually, I don't know what it says in the schedule for next week, but I booked another room for next week, because next week we have the practical work, which we will do either in the computer rooms at the Snellius building, or in the room where we'll be teaching. So we'll probably split up in two groups, and those of you who bring a laptop, and hopefully some of you will, they can stay in the room, and the others can go down to the computer rooms. And so next week we won't be having a lecture in whatever it was. I think Van Steenis maybe, actually. But we will be in this room, 407, 409, in Snellius. Does everyone know Snellius? I will put it on the website anyway. And please inform your colleagues if you know that they can't make it today, but they are thinking of coming next week, 407, 409, and we'll actually put up a note at the wrong room in order for you to, everyone to be there. So don't forget that. We'll probably start a little bit late, maybe 5 or 10 minutes then, so that people can come in, even if they got it wrong the first time. Right. Okay, so that's about the lecture room. Yeah, we're going to talk about decision trees today. Actually, we're going to talk about classification. So I explained 2 weeks ago that classification is one of the central tasks in data mining, and this is our first algorithm that actually tries to approach this task of classification. So maybe we should go back one step to what we were discussing last week. Last week we were talking about entropy. And it's probably good to have this entropy view on classification also. So we were talking about entropy of whatever attribute you come across. But in this case, let's think of a specific case where you have the class attribute and there's some entropy in the class attribute. That is, there is some uncertainty in the class attribute. If you look in your data, maybe half of your data might be true and half of it might be false. And that's the uncertainty that you want to resolve somehow. You want to predict something based on your insights. And as soon as you are able to predict it, there's no more uncertainty, of course. So before you actually do any analysis, there is some uncertainty in the targets, so in the class attribute. And we can capture the level of that uncertainty with the entropy of the distribution we have of the class attribute. So if it's a 50-50 distribution, for example, true and false, binary classification, we'll have one bit of entropy in the class attribute. Now, of course, we would like to resolve this uncertainty. So we want to get rid of this entropy, essentially. So we're going to ask questions, and we're going to take the other available attributes in the data set to answer those questions. So hopefully those other attributes will tell something about the value of the class attribute, so whether it's true or false. And if we just ask the right attributes for their value, hopefully we will get some information about the value of the class attribute, which will decrease the entropy in the class attribute. So that's what we're looking for. So we're trying to increase the certainty about the class by considering other attributes. And we do that one by one. We just take one attribute and see if we somehow condition on that attribute, which essentially means if you put a condition on it, that's one branch, and if that condition fails, then that's the other branch. So that will give you a split, right? And if you split long enough, you get a tree, which I hope you'll understand. So we hope that by splitting, we will actually go from a state where you have a big amount of entropy to a lesser amount of entropy. And yeah, we're going to measure this change in entropy, this change in information. And we're going to call that change, we're going to call that information gain. So that's the central term here, information gain. So actually going from a rather uncertain information to rather uncertain situation to a situation where you have much more certainty. Okay, so we're talking about decision trees. Let's just have a look at what those are and how to define them. So here's a decision tree that you've already seen. I'm not going to tell you how we got this decision tree. It just is a decision tree, so it's a classification model. So, specific thing about decision trees is that you will have these splits over here and over here, and the splits are always associated with a test on an attribute. So, for example, over here there's a split, and it's based on the question, what is your age? And if your age is above a certain threshold, then you go one way. If it's below that threshold, you go another way. And then each branch in the tree, so you can go left or right. So each branch corresponds to the answer to that question. At the end, we will have leaves. So there's kind of a tree analogy here with where you have a root and you have the branches and you have the leaves, of course. So at the leaves, you will either have a conclusion, which is yes or no, or if you're going to be more subtle about it, you're going to have a distribution over the possible values. So 90% is true and 10% is false. So what else do we have? I already mentioned the splitting. So over here, we take the attribute, in this case age, that will give us the best split, that will give us the most information gain, in fact. Okay, so then that's our tree, and if we want to use this tree to classify, of course, we've seen this before, we simply take a new case, run it through the tree, you answer all the questions that you come across, you end up at the leaf, and at that leaf you will have a distribution, or you will just have an answer, yes or no, and that's your classification, essentially. That's how you apply the model. Of course, we're not so much interested in applying the model, we're mostly interested in actually building the model, so that's what we'll look at. And we'll do that again with our fancy data that we have about playing tennis. You've seen this before. We have a target attribute that's on the right that in individual cases is true or false, but on the whole there's a distribution over true or false. Well, in this case it says yes or no, actually. And after some analysis steps and some data mining magic, you'll end up with a decision tree. And this is what the decision tree looks like on the play tennis data set. Going through an algorithm called ID3. And I will explain that algorithm in just a few slides. Actually. So what we'll see here at the top, it takes one single attribute from the data set that after careful analysis has come up as the best attribute to split on. In this case it has 3 values, so we have a 3-way split. And in one of the cases there's already a clear answer, so there's no more splitting necessary then, and in 2 of the 3 cases you will need to ask further questions. And what that question is on the second level depends on the branch that you're in. So you can associate each branch with a subset of the data. So at the top you have all of the data, and then here you have some subset. Within that subset, humidity makes a lot of sense. In another subset, windiness makes a lot of sense, actually. Right, so we're going to build decision trees. We're going to induce decision trees is the technical term. And this was something that was proposed, for example, by a guy called Quinlan in 1993, so it's a fairly old algorithm. Essentially it builds trees top down. So it's a bit confusing because trees generally grow bottom up, but let's say the technical term from computer science is that they grow top down, which means you go from general to specific. So actually most of our trees will either look upside down or they will look from left to right, depending on how I prefer to draw them. So top-down means essentially we'll start with the root of the tree, and that root represents the entire data set that we have, all possible cases. Then you make a split, and then you get into slightly more detailed data sets, so subsets of the original data set, and you continue that until you have very small cases. So top-down construction of decision trees. There's other ways to do it, but this makes a lot of sense. And actually, once we've built a fairly large tree, actually we'll do something which is called pruning. So you'll actually cut away part of the tree. There's good reasons for that, but I won't disclose those reasons this week. So you have a little bit of motivation to come next week to figure out why you would cut into a tree that you just carefully constructed. There's very good reasons for that, actually. Okay, so if we're going to build a tree, let's just start at the root, at the very beginning. What's the first challenge that we have? The first challenge, of course, is, okay, which attributes are we going to split on? We know that we want to split, but there's a whole bunch of attributes. Actually, all of the attributes except for the class attribute. That would be cheating, of course. So we need to somehow go through all the available attributes and decide for each attribute to what extent they correlate with the target. If there's a lot of correlation, then if we split on that node, then we'll gain a lot of certainty about the value of the target. So that's the information gain that we're looking for. Essentially we're going to take every attribute, compare it to the target, and have some sort of measure, some sort of function that will have a look at the data of the two attributes involved and give you a number of how good that split would be if you would split on that attribute. Now it's called a goodness function or a quality measure or an interestingness measure, all kinds of names for it, but the good thing to realize is that there's no one function that is ideal. You can think of a lot of possible functions to give a number to how good each attribute is, and there's a few obvious ones, but this is not an exact science. It's not clear which one of these functions should be preferred. These are some common names. I will discuss this one, and we'll start off with this one. It's called information gain. That's the actual name of it, and it kind of corresponds to the intuition that I gave you before. So if we're going to decide on which attributes to choose for our first split, what are good qualities? What do we want, actually? Actually, one of the heuristics that you could use is to say, okay, I would like to have a tree that's fairly small. I can build a very large decision tree that uses all of the attributes in the data set, but let's not do that. Let's focus on the attributes that matter, that will produce a small tree. And then actually what the heuristic here is that we want to have a splitting criterion, a goodness function, that will give us pure branches, and ideally in the end pure leaves. And pure in this case means either all positive or all negative. And if you're thinking of beyond binary classification, pure means all of the same labels inside one leaf. So pureness, that's something that we're going to go for here. Actually, that's the opposite of entropy. So if you have a lot of entropy, it means a lot of uncertainty. It's very impure because you have both positive and negative cases in one branch or one leaf. Whereas if you think about pure, that actually has no entropy at all. So these are the opposites of each other. Right, so I mentioned information gain, and this pretty much recaps what I said before. So we're capturing the entropy of the class attribute, and we're going to watch how that number changes when we condition on interesting attributes. And we're going to observe that when the information gain increases, we will see an average increase in purity as well. So ideally, we hope to end up with a tree that just has branches with unequivocal conclusions there. It's all positive or all negative. Whereas at the root you would have a mixture of these things. Okay, so we're going to build a decision tree that uses information gain, that's focused on purity, to pick the one attribute that gives us the best split, and then we'll just make that split and see what happens afterwards. So it's essentially a recursive algorithm. Now, I realize that some of you haven't studied computer science yet, so maybe you're not familiar with the term recursion yet, but essentially it means that you solve a task, you solve a bigger task by breaking it up into smaller tasks and then solving that task as well. So if you think of a decision tree, at the root you have the same kind of challenge as you have in the first branch to the left and the first branch to the right. You just have a slightly different data set. But the question is the same at that point again. Okay, now I have a new piece of data. What is the best attribute to split on? Then you make a split. Again, you have kind of a recursive challenge there. So top down, actually, in this case, corresponds to recursive. It's also greedy. Greedy is another computer science term, which essentially means is, okay, I have a big problem. I can go through a whole number of combinations to try and find the optimal solution to that problem. But let's just first solve a little bit of that problem. So we'll take one chunk of the problem. We'll give a solution for that chunk that seems good at this point. That's the greedy part. So we'll solve the question of, okay, what's the best first split? And then we'll see whether that gives us two new questions, two new challenges that can be easily solved or not. And in practice, it turns out that they can almost always be easily solved afterwards, but there are some exceptions. So the thing with greedy algorithms in general is, and I hope computer scientists agree with me, is that they're very good at solving optimization problems to a reasonable degree. So you have no guarantee that you will find the perfect solution, but you have a pretty good guarantee that you will find a very good solution. That's combined with the property that it's very fast. So you solve one part of the problem, then you take that decision, and then you forget about that part of the problem, and then you just need to solve the rest of the problem. So greedy algorithms, they're attractive because they're fast, and they give pretty good solutions. But if you want a perfect solution, then you need to take a different algorithm that doesn't work top-down, but that also takes years to compute, and whereas this is maybe a matter of seconds. So most people don't think about this, but we're making a choice here to go for a good solution rather than for the perfect solution. Right. So our challenge was, how can we choose the best attribute to split on? You may have noticed in the data set that there's actually 4 attributes to split on. They're called outlook, humidity, windy, and temperature. And our question at the top of the tree, the root essentially, which of these attributes works well. So yeah, essentially what we do here is kind of already try to make that split and see how it turns out. So let's say we split on outlook. Outlook has 3 values. We'll end up with these 3 subsets. And the question then is, are these pure branches that will end up if we make this split? And we can compare that to, for example, humidity. To what extent is this a pure branch or this a pure branch? We'll do the computation. We'll give some number to that, and at some point it turns out that one of these attributes is actually the preferred choice. But maybe let's see how you guys feel about it. So if you would have to split on one of these 4 attributes, which attribute would you choose?
Outlook.
Who says outlook? Yes. Why do you like outlook?
Since we have one pure attribute, overcast, which is
right.
only yeses in it.
Yep. So this is a school example of a pure leaf. It has 4 cases and they're all the same. They're all yes. So that's very attractive. However, this is not so pure, right? So we'll have something good here combined with not so good and not so good either. Is there somebody who prefers another attribute? Does everyone prefer outlook? Yeah?
Maybe humidity. Humidity has one case where normal equals no. And and the last column is 50-50 split. So I think that is that case has the highest entropy.
Yeah, it's not completely pure though. There's one no in here, so that's a small downside. But yeah, absolutely, this very defendable, which is a very defendable choice also. I guess you would agree that temperature is not much use at this point because it's all mixed and modeled, and that's not what we want to split on. So yeah, probably outlook, possibly humidity. It turns out to be outlook, but that's only after you've done the real computation that you figure this out. And yeah, feel free to compute it and prove me wrong, but I think it's outlook. So what do we have if we were to split on outlook? So yeah, we already observed that there's one pure branch, so that looks very promising. The other ones they're so-so, and in the end we'll have to balance these pros and cons a bit, right?